Okay, our next speaker is Devavrat Tomar. I hope I've pronounced the name correctly. Devavrat is a PhD candidate at the Swiss Federal Institute of Technology at Lausanne, or EPFL, specializing in data efficient deep learning. And his research revolves around data augmentation for enhancing test time adaptation, model generalization, and differential privacy. So very relevant to this workshop. Thank you very much, Devavrat, for accepting the invite. The floor is yours.
Can you hear me?
I can hear you perfectly well. Go ahead.
And you also see the slides?
Yes.
Okay, thank you. All perfect. Yeah, thanks for inviting me for this interesting workshop. And so today I would be giving my recent work that I did in a couple of years. And it's basically optimizing augmentations for test time adaptation. So like the basic motivation for test time adaptation is that deep learning models, they usually suffer performance degradation whenever there is a covariate shift, and it's a very known issue. And the remedies basically includes to have more robust training or have some generalizable models and other techniques like dropouts or weight decays. But these techniques may not be enough at test time deployment, because getting in to know a priori what kind of covariate shift can happen at test time is not feasible during training. So in order to overcome this, we propose optimal test time of the augmentation, and to tackle the covariate shift using two key ideas. So first is like when you want to adapt to a new test domain, you can either change the input images to lower the covariate shift. For example, you can simulate a source like image characteristics whenever you tackle a new environment. Or the second case is like you can adapt the model using self-training methods with adversarial augmentations. So to briefly describe the problem setting, so what we have is basically a source model, which is trained on a labeled data set. Let's say here some synthetic images using supervised training method. And then you kind of deploy it in the real world setting. And in the real world setting, the access to the source data set is not always possible. So techniques like unsupervised domain adaptations may not work. So what test time adaptation does is like you get the current images of the target domain, and you adapt either the images or the model to give a better prediction. So like if I see functionally, it's closely related to domain generalization, but it's it's different in the sense that you basically adapt the model in an unsupervised way on the current image, or you adapt the model. So with these two axes, like our first work was regarding finding optimal test time of the augmentation to adapt the input target images. And so what in this work, we propose to learn augmentation, basically the magnitudes, to simulate source-like image styles without changing the model parameters. And this kind of technique works well for medical imaging modalities like MRI or CT scans, where the domain shifts can be simulated using simple image transformations, like example, contrast and gamma correction. So to briefly describe our method called Opta, we have basically two phases. One is the exploration phase, where we get a let's say, a test or a target image. And we want to optimize because we don't know what magnitude of the augmentation I should choose so that the model performs well on this given volume. So we construct like a large number of policies, which is basically just a concatenation of simple image transformations like contrast, blurring, brightness. And then using this policy, you can augment the image. And now the task is like how to optimize or select the policies so that the model performs well on the augmented view of the current image. So in this case, we define this unsupervised kind of objective, test time objective that doesn't depend on the label, of course. And it comprises of like two basic loss terms. So the first term makes sure that the augmented view that we have, it simulates similar batch norm stats as are commonly stored in the deep model because they use mostly batch norm layers. So we want to simulate or we want to optimize augmentations so that this batch norm stats match. And the second term makes sure that the pixel segmentation, make sure that the class-wide segmentation is more uniform and confident, and which relates to information maximization. So this exploration phase is basically an expensive operations because you have to optimize individual augmentation policies and then select the one that works well. So to reduce this time complexity, we introduced this exploitation phase where the other images from the same domain, you don't need to run or explore the augmentation space again. You just take the top policies that were discovered in the first phase and just apply them as it is for final prediction, which is basically ensembling the output of the model on the different augmented views using the optimal augmentation policies. So, I mean, here in this figure, we show how the augmentations change over iterations. And on the left, this is basically a target volume, which you have to segment into three classes. And the model here is kept frozen. And what we do is then we sample the magnitude of a particular subpolicy using a uniform distribution that has two parameters, alpha and beta. So alpha kind of selects the mean of the magnitude of the augmentation, and beta is kind of simulating the variance. So if you sample and then do back propagate, you can optimize alpha and beta using the reparameterize. Yeah, it's like a reparameterization trick. And yeah, so we tested this method like on three modalities, not three modalities, like three different organs of the MRI data sets. And here we show how the augmentations policy evolved during their update. And so you start with the target image and the model predictions are very bad. And as you learn better augmentation, like the optimal contrast and the gamma correction, the final output gives you kind of perfect segmentation. So regarding the performance, like we found that just on this MRI dataset, by just using the right type of augmentation and right magnitude of the augmentation, like optimized using this L-opta loss, we can beat a lot of baselines, for example, unsupervised domain adaptation that needs basically access to the source domain, and other test time model adaptation methods like tent or pseudo labeling, as well as the other test time augmentation modules, for example, Randog, or there's another paper that optimize the augmentations, but they have like a limited grid search space. Also, because we are not updating the model parameters, we find that the calibration of the model on the augmented images is also very good as compared to model adaptation methods like tent or even the source model. And in the third figure, in the fourth figure, we also show like the confidence and uncertainty estimates, because now we have several augmented views. We can measure the uncertainty with respect to those augmentation, as well as the average confidence of the model on the augmented images. And we see that for our method, the most uncertainty is near the edges, which is acceptable, I guess. So like now, so what we did previously was like, okay, you change the style of the image using augmentation, but is it sufficient for all kind of image modalities? And can we use it for RGB like images and even for different tasks like classification instead of segmentation? And what we found in the preliminary experiments was that just augmenting the images at test time, even though it's optimal, may not be sufficient to reduce the covariate shift. Maybe it's because the augmentations are too simple and they can't make the target image look like the source image. So we introduced, so we worked on the second axis, which is like, why not we adapt the model itself on a harder augmentation, because it's easier to always increase the covariate shift with respect to the current target domain and make a harder augmentation than to reduce the covariate shift using and yeah. So like the main idea for this work was to use mean teacher as a proxy that can provide pseudo labels to train the student on the harder augmentations. So I'll explain what harder augmentations are. So like, as I said previously, so this is basically our main motivation. So let's say the current source model here has the feature distribution as shown in the both figures, and the model has a decision boundary, and the region near the decision boundary is like kind of an uncertainty region where it's not confident, and the error and most error come from this region. So there are some easy images, which easy images means the model is very confident, which is shown in the pink as a pink output. And for the hard images, the model is not very sure. So the pink histogram is like very uniform. So what we propose is to push the feature representations of all images towards this decision boundary, and try to update the model on the pseudo label of its unaugmented version. So by doing so, we see that for easy images, the difference between the pseudo label and the model's prediction on the augmented view is very large, and it can learn from its harder image augmentation. while the images that were already hard for the model kind of discards those updates as the KL divergence between the pseudo label and its output on the augmented image is close to zero. So eventually the model kind of learns to better classify harder images because the augmentations kind of simulate hard to classify examples. So our test time objective for training the model is inspired by flipped cross entropy loss. So instead of using the normal cross entropy between the pseudo label and the output of the student, we kind of use a flipped cross entropy. What is by flipped means like you just reverse the label and the prediction of the student. And by doing so, we see that this representation of flipped cross entropy is kind of similar to maximizing the mutual information, and followed by KL divergence term that kind of corrects the output of the student from the teacher. So here y hat is the output of the teacher and y is the output of the student. So it tries to make sure that it follows the distribution of the teacher along with the mutual information term, and which gives us this ugly looking loss function, which is kind of an approximation to the above. And the second phase, what we do is we also add this knowledge distillation term, which was our kind of a motivation. So here what we have is like the test images, they go to the teacher model, and the adversarial augmentation or hard augmentations, they go to the student model, and this is basically updated by the pseudo label. So here we don't need to filter out easy and hard images because that's kind of taken care by the assumption that these augmented images are in the uncertainty region. So the overall loss function then becomes the test time objective, which is like updating the model on the non-augmented images, followed by this knowledge distillation term on the adversarial augmentations. But now the question arises, like, how do we find those hard to classify augmentations? Basically, we call them adversarial augmentation. So we use same augmentation operations to be consistent with other baseline as defined by auto augment, but these augmentation operations are differentiable. So basically, we divide the augmentation policies, as in the previous work of Opta, into a combination of n image operations with learnable magnitudes. So if you see in the figure, we have like sub policies row 1, row 2, blah, blah, blah. And on the right, you have the magnitudes and the probability of selecting a particular sub policy. So a sub policy is basically evaluated if this loss term is low. And this loss term kind of measures the entropy of the teacher on the augmented view. So if the entropy is high, it means the augmentations are like the augmentations are near the decision boundary, and thus adversarial. So if a sub policy is able to push the feature representation to the uncertainty region, then that sub policy is good, and it should be selected more often, like its probability of selection should be higher. So but how do we optimize? Now the question comes is like, how do we optimize the magnitude and the probability of selecting an augmentation sub policy? So in theory, what we want to do is we want to minimize the expected loss over all sub-policies. It's basically, which is equal to just the probability times the loss of that given sub-policy on the current image. But to evaluate this expectation, you have to pass the images like mod p number of times to the image, and it's very inefficient. For example, if you have 200 sub-policies, then the adaptation time increases by 200 times. So in order to avoid that and have some efficient implementation, what we do is we find a sample gradient estimate of this loss function, which is derived, which is inspired by the reinforce method in reinforcement learning. So if you follow the derivation, the unbiased estimate for the gradient is basically comes from the two terms. So the first term is optimizing the magnitude, whereas the second term kind of optimizes the probability of that sub-policy being selected. So in a nutshell, what we do is we initialize the probability as uniform and the magnitude as zeros, and we sample randomly using this distribution, the augmentations, and optimize that particular sub-policy using this gradient. So if the sub-policy is good, in future it will be selected more often and with the correct magnitude. So this is basically the overall framework that we proposed. So in part A, we do adaptation on the normal images, which is basically mutual information maximization with the correction KL divergence term. And for the part B, we do knowledge distillation from the teacher to the student on the adversarially augmented images. So like we tested this method for like two tasks, as I mentioned earlier. One is the classification task and second is the segmentation task. So on the classification task, we use the common domain, common domain generalization benchmarks, maybe, which are like C/10C, C/100C, and ImageNet-C, which are basically the corrupted version of the original validation set. So in this, they have like 15 different corruptions, like motion blurring and Gaussian noise. And the second type of domain shifts that we consider was how it performs from synthetic to real images. So you train your model on your synthetic images that are simulations by the computer of objects, and then you try to test or adapt it on the real photographs of those objects. And we see that we are able to outperform previously mentioned test time adaptation methods. The third type, which is kind of an important for this workshop, is a measurement shift, what we call the domain shift that we observe in histopathology. And we also see that even though we don't use histopathology relevant augmentation, we just use the auto augment image operations, we are still able to do much better when adapting the model trained on one histopathology domain to the other. For the semantic segmentation task, we use the same baselines as in our first paper, and see that for the two organs, our method can also perform nice, also give nice performance on the segmentation task. And another segmentation task we did was on GTA5 to cityscape adaptation. And here also we observed that indeed, like training the model or self-adapting the model on adversarial augmentation is kind of beneficial. So we did a lot of stress testing for the method, like what kind of different backbones it can work on. And we observed that the method, you don't need a specialized source training strategy or any model architecture. It can perform well for different, like the transformer-based models or the ResNet 50. And on the right side, we show how the feature representation looks like for and compare it with another baseline at a contrast. And we observe that the clusters are separated much better for our case. Like another point that is important for test time adaptation is that whether you're able to preserve the model calibration and whether it can give you good uncertainty estimation. So in this case, also we see that Tesla is able to handle a model calibration well. So it doesn't necessarily give overconfident or underconfident predictions. So that's also a good point. Another test we did or ablation we did was to try this adversarial augmentations with other test time methods like tent, shot, and other contrast, and we see a consistent improvement if you use those adversarial augmentation module along with their respective test time objectives. So in conclusion, I would say that test time performance of a pre-trained model can be improved either by adapting the images via augmentations provided that the domain-specific augmentation transformations are known, because we see that even though Opta performs well for MRI dataset, it doesn't do well on histopathology images because you need to know what augmentations are optimal for the current domain. Or if you don't have this, then what you can do is you can instead adapt the model on even a harder augmentation and learn from those augmented views. And there are also many challenges, like two of them, the most I think should be addressed in future is the closed wall setting. So the current test time methods, they assume that the number of or the categories that are in the training set are same as the test set. So what happens if you have new categories? Will the model lose its performance on the in-distribution categories, or will it ignore those out of distribution categories? And the second thing is that it assumes that the test images are kind of IID distributed, but it means that they have similar sizes for each category. And I wonder if these methods, they perform equally well whenever you have a class imbalance, or when the images come so one after the other. For example, you just the model sees only one category A, and then after a while it starts to see category B. Whether the model will adapt itself or like kind of collapse by just adapting on all the target A images. So yeah, thank you. I hope you enjoyed the presentation.
Great, thank you very much, Devavrat. We all know that Tesla is a winner, right? It's a good. So we have time for maybe one or two quick questions, if anyone has any burning questions.
Yeah.
You want to try this one?
Okay, you have to keep it close to your mouth.
Try this one.
Okay. So this one works better. Okay. Hello.
Hi.
Devavrat, thank you very much for the great talk. So it's more of a general question. So we had another talk this morning talking about how you have to. So the original paper title actually is augment like there is no tomorrow by Juno.
Yeah. Yeah.
If you so what he did was just like looking through a bunch of augmentation and decided to really extreme bounce on the augmentation that he wants to use during the training. And in his experiments, he found that it's really effective. So I was wondering, in your experiments, you also try to include that kind of extreme augmentations and compare the results with this optimal finding set of augmentations.
Yes. So I think in the first, I also attended that talk. It was nice. In the first talk, it was important basically to know, if a model, you want to train your model in such a way so that it generalizes well, and you want to choose augmentations so that the model can it can give you good performance whenever there is a domain shift. Like different from that, the setting that I proposed was like you have an off-the-shelf pre-trained model. You don't know how it was trained. Of course, it can work well, but still, if it doesn't, you can still learn without any labels. For example, in the first, when you want to train from scratch, you have the labels available, and then you use the strong augmentation to train the model. In this second setting, we don't have the labels, but we have the pseudo labels, which are kind of noisy. And the idea is like to make sure that all the augmentations, they go towards this uncertainty region, so that when you update the model on those hard augmentations and the pseudo labels, the model learns only from like good pseudo labels, not the bad ones.
Yeah, makes sense.
So I see that similarity here. Yeah.
Yeah. Thank you very much.
Okay, great. Thank you very much again.
Thank you. How do I stop?